Good morning, I'm Liam Emmett and this is my standalone PV system design. This video will provide an overview of the design used for the standalone PV system for a small property in Moree, New South Wales. The system is set to be designed with cost efficiency in mind, allowing the owners of the property some financial safety. It's also been made clear that the system needs to be capable of energy storage, while also having 4 to 5 days of autonomy. The system must be able to make the property completely off-grid, so reliability is key. By inspecting the installation data for Moree, it's evident that June is the worst design month, as shown in the table. The reason for June being the worst design month is that the ratio of solar irradiation to average daily load is the lowest in June. Because of this, it seems logical to design the system based on data for June. While this may hinder how effective stronger months, such as January, are, it'll help the system reach the load needs of the system every month, not just summer months. The power ratings were found by searching for a suitable appliance for this household that fits under the necessary load bracket. For example, the hairdryer is only on for about 5 to 10 minutes each day, so it seems likely that only 2 people live in this property. And since only 2 people live there, it seems logical to have a drawer-style dishwasher, as opposed to a full-size dishwasher. By making this decision, the power rating of the dishwasher is lower than it would have been otherwise. Similar logic was applied to all different types of loads. Both the AC and DC load tables calculate daily energy usage in watt hours. It does this for both winter and summer separately. This energy is then divided by system voltage, in my case 48 volts, which gives the total load in amp hours. The PV system I designed has this table in both the DC loads and AC loads sheets, which gives you the average daily DC energy throughout the year, average AC energy throughout the year, system voltage, and the average load. This table is also fully automated, which therefore makes it easy to monitor the effects that changing an individual load has on the energy required for the system. This is the automated table with the formula for finding the system voltage shown above. Given a depth of discharge of 60% and a desired days of autonomy of 4 days, the selected battery is the ChargeX 12V 500 Ah lithium-ion battery. The reason for this decision was the high battery capacity at nominal discharge rate. To meet the needs of the design load energy, I needed 2 parallel strings, each with 4 batteries in series. The series strings brought the cell voltage up from 12 volts to 48 volts to meet the system voltage. The parallel strings brought the discharge rate up from 500 amp hours to 1000 amp hours. While the capacity of the batteries is slightly lower than the required battery capacity of the system, I'm satisfied that since the battery has 3.43 days of autonomy, only slightly less than desired. This isn't a huge flaw, since I decided long-term cost efficiency was the most significant factor for the system design. The 8 batteries cost a total of $40,000 at $5,000 per battery. The selected solar module is the Tindo Cara 290, which has a module power of 290 watts, short circuit current of 9.55 amps, open circuit voltage of 39.5 volts. The module was sized based on the worst performing month, June. The Design Excel program indicated that for the chosen module in June, 8 parallel strings with 2 strings in series required to meet the design load. This means the system has a total of 16 solar panels at a cost of $300 per panel, total cost of $4,800. While this panel is on the more expensive side, the company is Australian based and also offers a 10-year product warranty, making it a safe and therefore suitable choice for this Australian property. I also selected a 48V 20A Victron Smart Solar controller as the charge controller. To meet the needs of the system, 5 of these charge controllers were needed in parallel to reach the required minimum current rating. The 5 charge controllers cost a total of $975 at $195 per unit. They were selected based on their wide range of operating temperature to suit the Australian climate. The charge controller can operate between -30 and 60 degrees Celsius. The selected inverter was the 48V 3500 watt sine wave electronics inverter. This inverter was selected because it met the required rating of the system. It had a half-hour max rating of over 5,000 volt ohms, met the required rating of 4,800 volt ohms. It also had a continuous rating of over 4.3 thousand volt amps and a surge rating of over 13,000 volt amps. The inverter cost $3,883 and was selected for its reliability as well as the long warranty period offered. The total system, including the modules, batteries, inverter, and charge controllers, cost $49,658. Most of the money was spent on the energy storage. A cheaper alternative was on the table, but the storage efficiency of lithium-ion batteries is worth the additional cost for the system. Properties looking for long-term benefits, so the period of interest is 30 years when calculating levelized cost of electricity. The cost of the solar array was roughly $1,000 per kilowatt, and the capacity factor is recommended to be between 0.1 and 0.2 for PV systems. Therefore, over a 30-year period, the levelized cost of utility electricity is 187.8 cents per kilowatt hour, while the levelized cost of renewable energy is 420.4 cents per kilowatt hour. Thanks for watching.